Good morning, everyone. I am Kajal Kansal. Today, I am going to give a presentation for CMIS 2025 on CAMNet, a transformer-based Grad CAM network for lung disease classification. So here are the table of contents like abstract, introduction, challenges, CAD and CXR modalities, gaps identified, motivation, literature survey, dataset description, experimental design, results, conclusion, and references. Let us start with the introduction. As we all know that lung abnormalities are among the significant causes of death worldwide, causing 3.23 million deaths in the year 2022, according to the recent survey by WHO, World Health Organization. So, we need an accurate disease diagnosis, successful treatment, and management. It enhances patient outcomes, public health, and improved precision. There are various challenges also in this domain related to the accessibility, affordability, and ethical considerations must be addressed. If I discuss about the challenges in the manual examination, that what are the reasons due to which we have to switch to the other automated systems. So the challenges are like inconsistency in disease differentiation, legal issues, time consuming, low quality images are there, human error and limited accessibility, high morbidity and mortality rate due to late access, doctor patient ratio in remote areas is very low. So, due to these challenges, we finally switched to the CAD system, Computer Aided Diagnosis System. Basically, CAD system is the combination of the two popular technologies named artificial intelligence and computer vision. When we work on the computer technologies and try to train our models, our systems like the human brains to work to experience to enhance or improve the performance, then basically we are able to generate a CAD system for the automated diagnosis of the lung diseases. What are the advantages of CAD? CAD helps in mass screening programs, generating electronic health records, telemedicine and remote consultancies, processes huge medical reports, predictive analytics for disease risk, and also helps in assisting the doctors. These are the gaps or challenges which I identified during my research, like the diagnostic process is manual, biased, and less effective. Images which we collect are corrupted due to the presence of noise. Existing methods or the conventional methods have very low performance. Diagnoses are limited by intra and inter-operator observer bias, resulting in misdiagnosis. Vague and subtle appearance is challenging. Conventional approaches makes disease detection and categorization difficult and inaccurate. So what are the advantages of deep learning due to which we switch on this particular domain for working? There are various advantages like it automatically extracts useful information, it shortens the time needed for diagnosis, enabling better patient care, it increases the diagnostic precision, it improves medical health domain, it produces an automatic and trustworthy diagnostic tools. These are the related works which I have gone through during my research. There are various computer assisted methods which have been deployed to identify and classify lung diseases. And I discuss now if I discuss about the objectives of my research. Basically, it utilizes the transfer learning approach to address multi-class lung disease classification, a comparative analysis of CNN architectures, and GradCam visualizations for multi-class lung disease classification. If I discuss about the dataset which I have used, basically I have used a dataset for this study which consists of four categories: COVID-19, normal, viral pneumonia, and lung opacity. I have done the split of training and testing into 70:30. Here, the COVID-19 category consists 3,616 images, out of which 2,531 images are utilized for training and 1,085 images for testing. Normal category consists of 10,200 images, out of which 7,140 images are used for training and 3,060 for testing. Viral pneumonia category contains 1,345 images, out of which 941 are used for training and 404 for testing. And in lung opacity case, category comprises 6,000 and 1,200 images, out of which 4,200 images are used for training and approx 1,804 for testing. So basically this means that model addresses various diseases and is trained and tested equally for all disease groups. Basically, this is the experimental design which I have followed during my research. First of all, I have collected this data set which consists of 4 classes: COVID-19, lung opacity, viral pneumonia, and normal category. Then I have applied some pre-processing techniques to make my dataset appropriate for training the models. Then after pre-processing the images, I have used a data augmentation technique for making the dataset appropriate and increase the number. Then after pre-processing and data augmentation, I have used the fine-tuned architectures for the lung diseases classification. And by using those architectures, I am able to classify the multi-class classification of lung diseases in 4 categories: COVID, normal, viral pneumonia, and lung opacity. And finally, I have used different performances measures to find out the best model out of all the fine-tuned architectures. I have also used Grad CAM visualization for the good visualizations. So these are the experimental design I have put there. I have used hyper parameters which I have used. I have used first of all the transfer learning technique in which the models are already trained on the ImageNet dataset. This dataset approximately contains 14 million images and 22,000 classes. I have used the activation function, that is leaky ReLU activation function, as dying ReLU problem is there in which weight updation doesn't happen. So I have used the leaky ReLU problem in my fine-tuned models. I have set the batch size as 50 and 40 epochs I have run for training and testing my models. These are the performance measures which I have used to evaluate my models, like accuracy, precision, recall, and F1 score. And here are the mathematical formula for all these performance matrices. And these are the results of my fine-tuned models. Basically, the fine-tuned models which I have used during my research is VGG16, ResNet 50, Inception V3, DenseNet 169, and CAMNet, which is the proposed model and giving the best performance measures out of all. These are the values of the accuracy, precision, recall, and F1 score in respect of all these fine-tuned models. Here are the GradCam visualizations of my models. These are the actual CXR modalities which I have used. These are the GradCam visualizations for VGG16. This column is for ResNet 50. This one is for Inception V3. And these GradCam visualizations are for DenseNet 169. And this last column is for CAMNet. If I finally conclude my presentation, then basically this research shows that proposed approach of fine-tuning the CNN transformer can effectively classify pulmonary disease from CXR images. The CAMNet proposed in this study yields impressive results with an accuracy of 98.33%, thereby outcompeting traditional CNN-based models. We also use the GradCam visualizations which enlightens the model's decision-making process and increases its suitability for clinical use. These results highlight the opportunity to incorporate transformer-based medical imaging architectures that increase diagnostic performance and interpretability. The proposed approach can serve as a basis for future work, combining deep learning models with interpretability methods and ensure more accurate and explainable machine learning based diagnostics of pulmonary diseases. So basically this is the presentation for my research which I have done in this field. Thank you. These are the basically references which I have shared in this slide, which I have gone through during my research. Thank you.